Yeah.
Okay, Nemanja.
I'm somehow not able to do something here. This meeting is recorded by the host or participant. How does this not happen? Hold on. Okay, got it. All right. Okay.
All right, so let me do the introduction for people who don't know you.
Very good. Go
so
for it.
It's a pleasure to have Surjeet Rajendran to give us a talk about some new ideas on modifying quantum mechanics and testing it. Surjeet has been a PhD student at Stanford, has done a lot of very interesting creative work on connections of atomic physics and fundamental physics and how you use one to search for signatures of the other and so on. He has then moved to, it was Johns Hopkins first to as a postdoc and then second Berkeley, correct?
Yep.
And then after Berkeley, after the postdoc at Berkeley, you were hired as faculty at Berkeley, right?
Well, I was a postdoc at Stanford, then I got hired.
Stanford, sorry, okay, I forgot that one. And then you started your first faculty appointment at Berkeley and then moved back to the East Coast to Hopkins, right?
That's right, that's right.
So, well, anyway, without further ado, let's move it over to your corner and take it from here.
Great. Well, thank you very much. It's too bad I can't be in Davis in person. It's a group that I've really liked and visited fairly often. So hopefully this will end soon and we can actually meet in person. So this is some work I've been doing with David Kaplan, a causal framework for nonlinear quantum mechanics. So here is kind of the thing, right? Like, why would you want to modify quantum mechanics? What's the motivation? Why do something like this? If you think about it, quantum mechanics was a theory that was built on some puzzling observations that people made in the early 1900s. And literally, when you think about the rules of quantum mechanics, a bunch of dudes got together in a conference and they came up with some rules, right? That's the actual history. So why should it be that these group of humans come up with some rules that we think are completely immutable? Why should it be the absolute truth? So there's good reason to think why you might want to modify quantum mechanics. And if you want to think about modifying quantum mechanics, one can ask, what are the two elements, the central elements of quantum mechanics that you might want to play with? So in reality, quantum mechanics has really just two postulates. There is probability. It says that the world has certain elements of it that are fundamentally probabilistic. And then there is linearity, right? These are the two things that quantum mechanics is really built on. And so the question is, which of these do you really want to modify? Okay. So let's first go after probability. A lot of people have tried to modify quantum mechanics to eliminate probability. And these things have really gone nowhere. And I can pretty much tell you why, in my opinion, changing probability is a waste of time. So let's take into account, let's ask, why is there probability in quantum mechanics? And I would say that let us realize there are two very important facts about the world. First of all, if you take some finite system and you ask how many energy levels are there for a system below some given energy, okay? It's a fact about the world that a finite system below any given energy has a finite set of energies. Like you take a hydrogen atom, you pick some energy state, some random energy E. Below that, you have a finite set of energies. That's all the system is allowed to have. We can talk about why that is. It's tied to thermodynamics, et cetera, but except this is a fact. On top of that, it is also the case that the world has continuous observables and symmetries. That's also true. And I would claim that these two facts are actually in contradiction with the notion that you have deterministic observables at all time. Okay, so if you believe that every property of a system is completely determined all the time, that is going to be in conflict with these two facts about the world. So let's see an example of this. So let's ask this question. Could an electron in an atom have a well-defined position, right? So this is basically the kind of model that I had in my mind as a child. When you think about the electron in an atom, you think of it as a solar system, right? There is a proton in the center and there's an electron going around it. That's how we've always imagined atoms to be. Now, suppose that is true. Suppose that's how the world actually worked. What this means is that this electron has a well-defined position in the atom and it has a well-defined energy. That's your naive classical assumption. So you take that particular electron and now you apply a rotation to it because a rotation is a symmetry. And you would now get another state of the system where the electron is now in a different position. So effectively, the position of the electron has become something like a quantum number, if you will. And because there is a continuous symmetry, I can basically start with an electron having a well-defined position and well-defined energy and get an infinite number of states, effectively, by just applying rotation. So you get an infinite degeneracy, which obviously violates the assumption that you have a finite system with a finite set of energy levels below any given energy. So quantum mechanics fundamentally is a compromise, right? It basically sacrifices this notion of absolute determinism, where you say the electron's position is absolutely determined at all time. Essentially, you sacrifice determinism in order to preserve a finite set of energy states and continuous symmetries and observables. So if you look at all of the so-called proofs of quantum mechanics, which show how quantum mechanics is fundamentally different from classical mechanics, things like the Bell inequalities, the Koch and Specker theorems, the SSC theorems, all these things, they're basically leveraging this particular fact, okay? That you would, for example, the Bell inequalities, you think about angular momentum. What are the Bell inequalities making use of? They're making use of the fact that I only have a finite number of angular momentum states, but look, I can make a very large number of possible rotations. And indeed, you can then play that game and quickly show that quantum mechanics will give rise to predictions that you cannot have in classical physics. So in my opinion, if you're trying to eliminate probability as a fundamental fact about the world, you have to fight against these two facts. And in my opinion, it's not going to go anywhere. Linearity. What does linearity fundamentally mean? In quantum mechanics, linearity is a statement that the wave function does not interact with itself. So let's give rise to a very concrete example of linearity in quantum mechanics, and that is a Lamb shift. So let us look at the 2s and 2p levels of hydrogen in quantum mechanics. In quantum mechanics, what you see is that the 2s and 2p levels are exactly degenerate, right? If you, in fact, this degeneracy is only lifted pretty much at through QED corrections. So if you think about that for a second, it's a little weird, right? The 2s shape is this spherically symmetric shape, while the 2p shape is this dumbbell. And the fact of the matter is that even though if you naively thought about it, right? If you thought about it as a classical charge distribution, you might think that a spherical shape would give rise to some spherical self-energy, and a 2p dumbbell shape would give rise to some, charge distribution that if it interacted with itself would give rise to some energy shift that depends upon the shape, right? So in quantum mechanics, since the electron's wave function does not interact with itself, the 2s and 2p levels are exactly degenerate. There isn't a shape-dependent correction to the energy of these two states.
Can I ask a question? Sorry.
What?
Can I ask a question?
Yeah.
Let's try to solve the Schrödinger equation.
Yes.
For the electron and the nucleon, that's hydrogen, let's say. Then normally we solve it, we assume a particle in the central potential, which means the electron wave function. But if we also treat the nucleus, the neutron, but like the proton, also treat that as a wave function. If I write down a Schrödinger equation, involve both the wave function of the electron and the wave function of the proton, the equation should be nonlinear, right?
The equation is linear, yes.
Then I would say this is called linear reality, the quantum mechanics. Sorry, that's my question.
That is still linear quantum mechanics. It just is an interacting theory now with the proton and the electron, right?
I think it just means that the wave function is linear. You can superimpose wave functions and the different components evolve independently. It's not saying that it's linear in the sense of no interactions. Linear in the sense that you could superimpose, for example, these two states, Lamb shift and
you mean
the 2s and the 1s, and they would evolve completely independently.
Okay, you mean without the interaction in the linear, right?
No, with interaction, with electromagnetism, right? That is interesting to think. If you take,
but what I'm trying to say, the dynamic, the Schrödinger equation, if you involve the wave function of the proton, wave function of the electron, the dynamics is the equation, the Schrödinger equation involved both wave function, is nonlinear. Do you agree with that?
No. The interaction between the particles is of course nonlinear. That's electromagnetism, right? But the fact of the matter is that it's still linear evolution of the full quantum system.
Linear in the full wave.
Okay.
The whole full wave function depends very non-linearly on all the coordinates. But the full wave function, if you take wave function 1 plus wave function 2.
Okay, I think I got it. Okay, thank you.
Yeah.
Okay. So now you can ask, right, is there a deep physical reason why somehow the shape of the electron is not something that is visible in quantum mechanics, right? But that's not true. If I put a second charge particle in the system, the second charge particle is very clearly sensitive to the shape of the electron cloud, whether it's 2s or 2p, because if it's a 2s electron, I put a second electron next to it, it will see a very nicely shielded nucleus. A 2p will see a slightly less shielded nucleus, obviously because the shape is different, right? So a second charge particle pretty clearly sees the shape of the electron cloud, although the electron cloud doesn't feel it itself. So it doesn't seem like somehow the shape of the electron cloud is a fundamental physical thing like probability that should not be somehow observable, because it clearly is observable. So let's ask, what can we do to make quantum mechanics non-linear, right? Non-linear in the wave function itself. And there's not been very much work done on this. There's only some work done by Weinberg back in the day. And the proposal that he had all kinds of causality problems. So the question really is, can we come up with a theory of nonlinear quantum mechanics that is causal? And how can we think about measurement in this case? And how can we actually incorporate everything in quantum field theory? Because at the end of the day, it's field theory that's really relevant to the world. So why should there fundamentally be a problem between causality and nonlinearity? You know, why did Weinberg run into this trouble? If you've never heard about Weinberg's paper, that's okay. We can just talk about what the answer should be. So at the end of the day, let's just look at classical physics. In classical physics, in a nonlinear theory, causality is, of course, enforced by some Green's function, right? It basically says if I shake something here, something else happens. As long as things propagate via a causal Green's function, everything is okay. Now, here is kind of an interesting fact. Linear quantum mechanics, as it's normally phrased, is, of course, basis independent. That's the whole point about linearity. There's no preferred basis as far as the formulation of quantum mechanics is concerned. You can take any basis you want. But there's an important fact about our world in the sense that in our world, interactions are, of course, local. That means interactions prefer the position basis as a natural place to think about stuff. So when you think about things like causality, which has to do with space-time, it would make sense to try to think about modifications of quantum mechanics that depend upon a specific basis, where some basis is more preferred, like the position basis. And if you think about it that way, you sort of realize that many of these issues can be resolved because causality, of course, is fundamentally tied to locality, which if you think about position basis is a natural way to think about it. So let's think about how we can try to come up with a nonlinear modification of quantum mechanics in the position basis. And it'll turn out this naturally blends itself into local field theory because, of course, field theory being formulated in position basis. So here's the outline of the rest of my talk. I will spend a bunch of time talking about the overall framework. We will talk about the field theory, the Schrodinger equation, and causality and measurement, these issues. After that, things will be kind of interesting in the sense that nonlinear quantum mechanics will turn out to have some extraordinary macroscopic effects, much more so than you might have naively guessed. And then we'll talk about constraints and tests of these kinds of scenarios and of ongoing experimental work. In a very weird way, it will turn out that nonlinear quantum mechanics is fundamentally extremely sensitive to cosmology. This is one of our main results. And I think this particular aspect of it is true no matter what nonlinear modification you have in mind. And so we will discuss that as well. And then I'll conclude. Surjeet,
can I just interrupt you very briefly?
Yeah.
Just to clarify something, you said that some bases are more preferred than the others, but surely you meant are more preferred because of habit and not necessarily because of anything intrinsic to them.
Oh, there is, right? So if you, for example, think about it, right? Like if you think about measurement in general, and this comes about all the time, right? Why do we generally see people sitting in a specific position and not in a superposition of position and momentum? So if you think about naive quantum mechanics, linear quantum mechanics, you could have written down Hamiltonians that are superpositions of position and momentum, like x plus p, right? As the linear mathematical thing, you can write that down. But interactions in the world are always in position basis. They're local. So this is a fundamental reason why when you think about quantum mechanics and what you can observe and what you cannot observe in quantum mechanics.
If I perform a canonical transformation in classical mechanics, I can do the similar thing in quantum mechanics as well. I'm just going to say that interactions will be, transformed to some funky basis. They just will look ugly. So to me, that's a matter of convenience.
No, but I'm asking a very simple question. So this goes down to things
I'm not really arguing with you. This is not a criticism. To me, it sounds that, some of it, what you're saying sounds like essentially a kind of heuristic / force of habit thing. It seems like correspondence principle. If you want to make a contact with classical physics, seems to work more easily with certain variables than the others. That's all I'm saying. That's all I'm trying to clarify. Because, if I did some canonical transformations, I could, in principle, I would get the same physical observables to come out regardless which variables I'm using.
Look, it is true that in linear quantum mechanics, right, because it's linear, you can make any transformation you want. I don't disagree with that.
Sure.
What I'm saying, indeed, is the fact that the question I'm asking is a little bit different. It's like asking, what is it about classical observables that's what we see in the world, right? Like, in other words,
correspondence.
Quantum mechanics,
good.
Yeah.
Good. It's the fact that Bohr formulated quantum mechanics by correspondence principle that kind of prefers certain variables rather than the others. But
I would
anyway, I won't bother you now.
Interactions are local. The classical world is something that is extremely, in a sense, preferential to position as a natural thing because interactions are local.
But again, that's just a language, I think, that you can basically, think about harmonic oscillator. I write down P squared.
It comes down to this simple question, right? Why do I see cats that are either dead or alive, but never a cat that is dead plus alive? Why?
Yeah, anyway, I'll let you continue.
All right, we can talk about it afterwards. Yeah. All right, so let's talk about the framework. What are we talking about? So my story will fundamentally be tied to field theory from the very beginning. Okay, so normally we think about field theory as something that sits on top of quantum mechanics. I'm going to start with field theory from the very beginning. All right, because for me that's an integral part of the view. So I'm going to use a Schrodinger picture of quantum field theory just to formulate this idea. So what do we do in field theory? In the Schrodinger picture, we say there is some wave functional. Okay, there's just a quantum state chi of t, which is a quantum state of all the fields. You can put it in some Fock basis or whatnot. And then if I have a scalar field theory, there are some operators, phi of x, that live on that. And then you construct a Hamiltonian, which is an integral d cube x of a Hamiltonian density, which is a function of both the field phi of x and its conjugate momentum pi. And in field theory also, even in relativistic quantum field theory, the quantum states chi evolve as per the Schrodinger equation I d chi dt equal to h chi. That's what you're solving. That's still the Schrodinger equation. Now I'm going to do something a little bit bizarre, which you don't normally do in linear quantum mechanics because this particular step doesn't buy you anything. It just helps me for nonlinearity, which is that I'm going to observe that this particular Schrodinger equation, I d chi dt equal to h chi, can be obtained by performing the Euler-Lagrange procedure on this action. So this is not the usual standard quantum field theory action that you're used to. I'm just making this up because it makes life a little bit easier in terms of introducing the nonlinearity. So this action is a function only of time, and it depends upon the the quantum state chi. So clearly, if I take this particular action, you can easily convince yourself that if you perform the Euler-Lagrange procedure, you will end up getting the Schrodinger equation I d chi dt equal to h chi. I have not added any new content so far. So let's take the Yukawa theory that we know and love. There is a fermionic field psi and a scalar field phi, and that's the Hamiltonian for it. What does this action look like? Well, this action looks like what is written on that screen there. And the Yukawa coupling y phi of x psi bar psi appears as this integral d cube x in the Hamiltonian, that is this coupling y, and then essentially there is a chi of t, which is the state sandwiched between this phi of x psi bar psi, right? So essentially, if you look at this action that I constructed from which you can get normal quantum field theory, what you're doing is you're taking the operator phi psi bar psi and computing its expectation value and then doing this integral. That's all you're doing. This, of course, gives you the usual Schrodinger equation. Now, in quantum field theory, we, of course, have no problem adding higher dimension operators in this particular picture. We all think it's very reasonable for us to look at higher order terms, phi square over lambda, psi bar psi, so on and so forth. So for the last 100 years, we have been studying nonlinear operators in the theory. but not in the state, right? The states in quantum field theory are still linearly evolving. They still satisfy I d chi dt equal to h chi, but the operators, I can put all kinds of non-linearities. Great.
Just a clarification. I just lost this somewhere. What is Y?
Oh, Y is just the Yukawa coupling, that's all.
Oh, okay.
Sorry.
Not a variable. Okay.
Yeah, sorry. Yeah.
Okay.
Yes. Now, if you look at this linear quantum field theory thing, there's a chi of t, phi, psi bar, psi, chi of t. That's just the expectation value that I'm computing. But this action just needs to be a number, right? So there's another way for me to get a number here, but I put a term epsilon up front. That's my nonlinear action that I've written down. And instead of writing chi of t, phi, psi bar, psi, chi of t, I can now write it as a chi of t, phi, chi, psi bar, psi, chi. So essentially that's a number, right? So there are many ways in which I can convert a matrix to a number here. And what I've now done is basically sandwiched a chi of t in the middle, which allows me to write that particular term down, right? So that particular term that I've written down is now nonlinear in the state chi itself. This, of course, obeys all the standard rules that you might care about, Lorentz invariance, stuff like that. It's just higher order in the states. And if that term existed, it leads to state-dependent quantum evolution. It's now nonlinear in the states chi. That's the main idea. And we're going to think about everything in perturbation theory. So essentially, I'm going to take epsilon to be small. So I'm going to use linear quantum evolution as the standard evolution and compute corrections using perturbation theory. It's as simple as that. So what does this do?
Okay, sorry. Can I go to previous slide?
Okay.
So where is this nonlinear quantum field theory coming from?
Where is it coming from? I just put it in by hand.
Okay.
Right. So your linear quantum field theory just contains the term S, right? That's linear quantum mechanics. And I'm telling you, look at that particular expression. All you know is that that action that I've derived there needs to have some numbers, right? That's all you really need. And I need to convert an operator to a number. To convert an operator to a number, I take an expectation value. So you were happy with me taking the expectation value, chi of t, phi of x, psi bar, psi, chi. And now I'm saying, look, there's another way in which I can get a number, which is to put an epsilon, chi of t, phi, chi of t, psi bar, psi, chi, right?
Okay.
So let's think about what this term will do in how do we analyze this non-perturbatively. So of course, I'm still solving the same set of equations, right? I'm going to take my action and I'm going to derive the Hamiltonian from it and compute the Schrodinger equation. So if I just look at how the psi field evolves because of its interaction with phi, the Hamiltonian gets converted into the usual y phi psi bar psi. That's the usual Yukawa coupling. But now there's an additional term, an epsilon chi phi chi. That expectation value lives there, right? That's what this thing is going to give you. So, and I'm still going to evolve the Schrodinger equation now. It's just that h now depends upon epsilon. It depends upon chi in this nonlinear way, right? So again, at zeroth order, when epsilon is 0, this is just standard quantum field theory. You know how to do it. And so what we're going to now do is basically to compute the first order correction, the order epsilon correction, I'm going to use a zeroth order solution, which is the usual standard quantum field theory thing, compute what the state should be, compute the expectation value. When I compute the expectation value, what it's going to look like is that chi phi chi is now simply a background field. That's what it is, right? I've computed how the state chi evolves. Take the expectation value. This is now a background field to compute my order epsilon correction. So essentially what you're going to do is you're going to perform standard QFT now on this background field to compute the first order correction. It's very well defined. And of course, this procedure will apply to all orders, because if I want to compute a term to any given order, I only need lower order terms. And all the lower order terms appear in this expression simply as background fields. And so once you've computed all the lower orders, all the lower order terms, the next order term will simply appear as a background field. And we know how to do that in quantum field theory. Let's think about causality. Why is this theory causal? Well, the simple answer, I can give you a more detailed answer. The simple answer is that if you think about it, nonlinearity in the story only enters via an expectation value. Now, at the zeroth order, right? At the zeroth order, the expectation value of the quantum field is, of course, causal. Quantum field theory guarantees that this expectation value will be causal. It's an observable of quantum field theory. And so when you want to compute the first order correction, right? Because the zeroth order terms are all causal, the first order correction will also automatically be causal. And you can just build that perturbatively to all orders and show that the theory is causal to all orders in perturbation theory. That's kind of the basic idea. Let's look at the single particle version just to get a feel for what this theory really looks like, right? So how does a fermion psi evolve? So suppose we have a psi particle. What does this thing look like? The single particle picture. It has a Yukawa coupling y phi psi bar psi, and then this is a y phi epsilon chi, this expectation value psi bar psi. How does this wave function evolve? Well, we know how to do this. At zeroth order, psi just sources the phi field, right? I have a fermion psi. It's got a coupling to a Yukawa scalar field phi, and all I want to now do is compute the expectation value of the phi field because of my fermion psi. And so at zeroth order, psi just sources this phi field. And so I can go ahead and compute the expectation value of this thing. And now I'm going to compute how this just changes the evolution. So what is that expectation value? This is just some chi, phi chi, this expectation value. And the calculation is very simple. This is just a charge density of the psi, right? Whatever the wave function of psi is, that gives rise to some charge density. And that charge density is what is going to appear in this expression with the Green's function clearly, because this is just standard quantum field theory. And that Green's function is going to be causal, right? No matter what, that Green's function that you compute in the expectation value is causal. So that you just plug that in, right? So that just gives you the single particle evolution now. So one thing that is a little bit different in our story compared to normal quantum mechanics is that the way in which the non-linearity appears is pretty clearly dependent upon the field. So in the case of the Schrodinger equation for the Yukawa theory, this is the single particle nonlinear correction. If I had given you a different theory, the 5-4 theory, something like this equation would clearly depend upon what that theory is, because I'm constructing these observables, these modifications from the existing interactions in the theory. So, but this is what it does in the case of the Yukawa coupling. So let's think about what the effects are going to be in the case of the Yukawa theory. So if I give you the simple problem, right? Like if I take a fixed central particle, like I take a proton, I hammer it to a location, and I'm going to compute the 2s and 2p level, like the Lamb shift, the thing that we talked about. What does this theory look like? In this theory, what happens is that if I take the 2s and the 2p levels, the 2s will, of course, be a classical charge distribution, the psi star psi, and it will source this Yukawa coupling, and the Yukawa coupling will give rise to a self-interaction, which basically will lead to the 2s and 2p levels having different energies. I've broken the degeneracy of the standard linear hydrogenic atom because I have this particular thing. And you can verify many other nice properties that this Hamiltonian I've constructed is actually Hermitian, stuff like this. So you can maintain the probabilistic interpretation of quantum mechanics and all that stuff. Those things work properly. Let's now talk about entangled states.
Why doesn't your argument work for the photon?
What?
The interaction there is from exchanging photons.
Yeah, it works with, well, in linear quantum mechanics, it doesn't, right?
It's a potential, which is a zero energy photon propagator.
Yes, but that only gives rise to an interaction between the proton and the electron, not on the electron to the electron itself.
But the question is why the potential does not depend on the wave function of the electron and the proton.
In linear quantum mechanics, right, what you do is that you go to the so-called center of mass coordinates, in which your potential only depends upon the relative coordinate V of r. And if you now go ahead and compute the hydrogenic energy levels, you will find that the 2s and the 2p levels are exactly degenerate up to QED corrections.
Yeah, that's great. I'm trying to say, if I understand correctly, what you are trying to do is saying, adding in the second term, the interaction term depending on wave function of the electron and proton. Is that what you are doing?
The interaction here is between the electron and it is between the electron itself. There is no, this term, the psi star psi, is the electron talking to itself.
This psi is only electron wave function.
Yes.
Your proton, I'm trying to understand. What's the wave function of proton?
What's the wave function of the proton? So
Yeah.
I'm saying fix the proton, put it at a point. Okay.
Well,
The proton gives
that's the way. I'm trying to say, yes, that's an approximation, right? You quantum mechanics, you cannot put a proton in a point, right? Proton, yeah,
This is basic first year quantum mechanics.
I know, I'm just
Go
trying
to center of mass coordinates. All that matters is the relative position.
that I know, I totally agree. I'm just trying to say, you are treating proton at the rest, right? I'm correct. You are treating a fixed position proton, right? But why proton?
Go to the center of mass coordinates. If you go to the center of mass coordinates, you can ignore the, then everything just depends upon the linear on the relative coordinate, right?
Mm.
And then you will find that indeed, while there's an interaction between the electron and the proton, the electron and another electron, the electron does not interact with itself. That's a fact about linear quantum mechanics. And in my theory, now it will, because of the fact that I've turned on this nonlinear term, which actually will make psi talk to itself and give rise to this kind of splitting.
That I totally agree. There's no interaction between wave function electron and electron. But I'm trying to say, if I treat the proton as a wave function, not at a fixed point.
Are you questioning the fact about linear quantum mechanics that in linear quantum mechanics, the two...
I'm just confused. Maybe just a very basic confusion. I'm just confused the following. This is linear reality. You're saying that the first class, first degree of the quantum mechanics. You are saying we go to center mass frame and we the potential only depend on R, does not depend on wave function of electron, wave function of proton.
Yes.
I'm trying to say, is this an approximation or is it just
it is just true. It is absolutely true. It's not an approximation.
It's absolutely true, not approximation.
It's not an approximation. No.
Okay.
Yeah.
I guess
that is why the Lamb ship is such a sensitive test. All right.
Yeah, why is this different from a mass renormalization, the way you've written it?
The mass renormalization, well, because 2s and 2p are now different, right? I will now get a contribution to the energy that would go as 1 over r, where r is the Bohr radius, as opposed to something like the, so I mean, if you do this more carefully, you can do counting in terms of alphas and stuff like this, and you will in fact find that this is this thing is an infrared effect having to do with the size of the electron wave function, as opposed to the usual Lamb shift. The usual Lamb shift comes around because of the fact that at the location of the proton, because of the loops that you're drawing, you're getting a new contact interaction. So you can actually compute how this correction depends upon powers of the wave function, powers of alpha. And you will find that this is a different power of alpha than the standard Lamb shift. Let's talk about entangled systems. Okay, so this is one of the things that actually caused Weinberg to stumble. So quantum mechanics cannot exist without entanglement. And so here is the issue, right? You take two quantum systems, I'd say two particles. One of them has a coordinate x, the other one has coordinate y, and they're entangled like so, Cij, alpha I, beta j. And you can ask, how do multi-particle systems evolve in my theory? And the reason why you might worry about this is basically that when you have an entangled state, let's say I have one electron here and there's another electron that I create some entanglement in the beginning, and then I take one electron, sit on the Earth, and the other electron, you take it and you go to Mars. And then you apply some local operation in Mars. What you want is that whatever local operation you apply on Mars cannot possibly change how my electron should locally evolve immediately, right? It's okay for it to evolve with the Green's function, that's fine. But if whatever I do in Mars immediately changed what was happening here, that will be a violation of causality. So if you don't put in the nonlinearities sensibly, and this is what Weinberg didn't do, then it can be the case that if you apply a local operation far away, due to nonlinear terms, right? I'm writing down psi squared terms of this kind, a local operation in one place can in fact change my time evolution. So let's now look at, in my theory, how does it work? How do I figure out what is the correct causal evolution Well, all I'm going to be doing is that I've given you the prescription. All I do is take my multi-particle system, and the nonlinear evolution happens simply by constructing a expectation value. You go ahead and calculate that. And this is what that expectation value is. I can just compute this from linear quantum field theory. What you notice is basically that this expectation value has this particular form, that it's some integral d cube x1, d cube y1, the wave function squared. And then there's a sum of Green's functions. It basically says, oh, I have my particle at x1, I have my particle at y1. The way x1 will affect x is by this Green's function that goes from x1 to x. And then x1 can also affect y, but that's again through this Green's function, this causal Green's function. Similarly, from y1 to x is a causal Green's function. Y1 to y is also a causal Green's function. So because this Green's function is basically baked into the system, you can, again, go and verify that causality is naturally preserved in the story. And there is a nice element of this, which is that when Weinberg had initially proposed his nonlinear quantum mechanics, the theory turned out to be acausal. And Joe Polchinski actually figured this out. And he came up with this prescription. He said, look, quantum mechanics could be nonlinear and causal as long as these non-linearities are affecting each other in multi-particle systems additively. So this is what I mean by additive, in the sense that you kind of see, right? The way the non-linearities are talking to each other is that, well, I go from x1 to x plus x1 to y plus y1 to x plus y1 to y. They're not multiplying each other. So Polchinski had actually shown, quite independently of anything that I'm saying, that if the non-linearities satisfied that particular rule, the theory would be causal. And in Polchinski's case, he just had to guess. He just had to show, well, this is what would work. What we see is that in this field theory way of thinking about it, this is totally natural. I didn't have to come up with it independently. I just put it in, it just flows out.
Can I ask the question?
Yes.
Is that only true to linear order in epsilon?
No. So Polchinski's claim was that to whatever order, as long as these things are, sort of additive, it will always work.
No, I mean, is it additive? Because it seems like at order epsilon squared, maybe I'm not following the sense that it's additive. I know Polchinski says
you will, if you go to order epsilon squared, things of this kind, once again, right, in our theory, as long as things to the previous order are going to be causal, and the next order too, it will be causal. So I've not written down the exact form, but it probably involves something more complicated. But I don't see any reason fundamentally why it would become acausal all of a sudden, right? Because I'm building everything causally at every order. Let's talk about measurement. This is something that trips up people a lot. So measurement is not some mysterious process. We have understood measurement very well for the last 50, 60 years, even though we don't teach it properly when we teach undergraduates about this stuff. And so this is what measurement is. What is measurement? What are we actually doing? We take a quantum state psi. Let's say it's a spin in some direction, okay? And I want to measure it. What I mean is that I have a measuring device, which I have initially localized to some state. There is some arrow pointing in some direction. And what we literally then do is that we take our spin and we bring it in contact with this measuring device. And the two of them will undergo unitary Hamiltonian evolution. The unitary Hamiltonian evolution in general will place this system in a linear superposition in linear quantum mechanics. So with some coefficient alpha, it will be spin pointing up, and the measurement device, the arrow turned to the left. And with coefficient beta, the spin points down and the measuring device points to the right. That's a prediction of quantum mechanics. So in general, when you're trying to do measurement, you're basically taking a quantum system and some measuring device that's in some initial state. And you do time evolution, which gives you this complicated linear superposition. This is a prediction of quantum mechanics. It gets a stupid name called many worlds interpretation, but it's not some interpretation. It's an actual prediction of quantum mechanics. There's something else you've learned about, which is called the wave function collapse, which in my opinion is just ridiculous. And we should just stop talking about it because we actually understand what quantum measurement in fact is. So this is what measurement is in quantum mechanics. It is the fact that I create entanglement between a quantum state and a measuring device. Now, in reality, what we actually do is the fact that when I think about this measuring device, if I want it to be a useful measurement, I pick the basis states of my measuring device so that the states AI and AJ are orthogonal to each other. I'm doing it out of convenience because that's what I would like to think is measurement. So when I choose that as my interaction, I realize that if I now, after creating this entanglement, if I solely focus on the spin, then of course in linear quantum mechanics that will be described by the reduced density matrix, which will be the sum Ci squared of II. Those are the states of the thing. And that is just an interpretation. This complicated density matrix effectively behaves as a direct sum of different worlds. Okay, that's just the way we think about it. But in reality, what is actually happening is that anytime I create this measurement device and I create this entanglement, I get this linear superposition. That is what quantum mechanics predicts. There is no such thing as a collapse of the wave function. This entire state exists. What about nonlinear quantum mechanics? I'm not going to change anything. It's exactly the same thing. I'm going to have a quantum state and a measuring device, and I'm going to bring them in contact with each other, which will then allow this quantum state to evolve as it's supposed to evolve. So I will now end up getting a complicated superposition. Now here comes the extremely interesting difference between linear quantum mechanics and this nonlinear theory. In linear quantum mechanics, right, if I want to make a measurement, I don't need to know anything at all about the coefficients of the state I'm trying to measure. Because that's the whole point. I don't know what state it is. I want to know, I mean, I don't need to know what the state is. All I need to know are the basis vectors of the states and the basis vectors of the measuring device. Once I know the basis vectors of the state and the basis vectors of the measuring device, I can create a Hamiltonian that will give me what I want. That's what I do in the lab, right? So no problem. In nonlinear quantum mechanics, I cannot quite do that. Because in nonlinear quantum mechanics, of course, the evolution depends upon the unknown state. So of course, if I knew what state it was, I could come up with a measuring device that does some interesting thing. But in general, right, if I give you a random state, I don't know what state it is. Since the evolution depends upon the state itself, I cannot guarantee that when the system time evolves, it will be the case that there is this nice split. Right? In linear quantum mechanics, I can guarantee that the state evolves as a linear combination of Ci, I tensor product with the AI, but the AI and the AJ are orthogonal to each other. I can guarantee that. In general, I cannot do that because I don't know what the state is. So I'll in general get this sum Dij, Iaj, but there's some kind of crosstalk between different elements. So essentially, this is some kind of fundamental measurement noise, in the sense that once there is nonlinearity, I'm not allowed to know with absolute certainty what the true quantum state is. There will be some kind of measurement. But that's just a fact about the world. I mean, if the world works this way, this is exactly what happens. That's the overall framework. And now we can extend this pretty easily to both gravitation and electromagnetism as well. In gauge theories and gravitation, of course, we don't want to use the Hamiltonian formalism because it's clunky. So you want to just do the path integral formalism. And the path integral, it's pretty easy to turn these things on perturbatively. So what you're going to do, for example, is that you take your action, and in electromagnetism, for example, I can add this term epsilon expectation value of f mu nu, okay, in the kinetic term, for example. So that's something you can do, and then put another f mu nu over there. And essentially what I'm going to do in terms of defining this path integral is that to zeroth order linear quantum field theory, I do my usual evolution. I then compute this expectation value of chi, f mu nu chi. That now gives me a background classical field, and I feed that background classical field to compute the order epsilon correction to the path integral. Okay, and that gives me the nonlinear evolution. You can show that this is exactly what would give rise to the Schrodinger evolution picture that I sketched out earlier for the scalar field as well. And for gravitation as well, you can do something very similar, where you basically, for example, can add expectation values of the metric into the path integral and define it that way. So it's not too difficult to extend this to gauge theories and gravitation.
Maybe one naive question. Can I go to previous slide?
Yeah.
The action. So the state chi, does this total action preserve Lorentz invariance? I mean, if I calculate any amplitude in the UV, does we have some subtlety or?
Well, if chi, what this will do is that this is a state-dependent evolution, right? So if chi is the vacuum, of course, all these things are zero. So in the vacuum, of course, this is Lorentz invariant. Okay. Now, if it's not the vacuum, you will have state-dependent evolution, of course, but it's still causal. That's exactly what we showed.
Okay.
So now let's talk about some of these macroscopic effects, right? So far you guys have been listening, and you asked, you sort of respecting me like a reasonable person. But now you might think, oh, poor Surjeet, he's gone crazy, right? The pandemic made him nuts. And, as many of you have known me for a long time, I've been crazy for a long period of time. The pandemic didn't have much to do with it. So you're going to see some crazy stuff here. But the crazy stuff I'll point out comes not even from me. It doesn't even come from my theory. It really just comes from quantum mechanics itself. All I'm doing now is studying the mathematical consequences of this very, in my opinion, well-defined formalism, for which I can see no obvious reason why it's wrong, right? I can just say, look, it preserves causality. I can even extend it to gauge theories. Let's see what the consequences are. That's all. Let's talk about linear quantum mechanics. In linear quantum mechanics, suppose I take a spin and orient that along the x direction, all right? And then I've got an experimentalist, and then I've got a laser with two photodetectors, one to the right and one to the top, as I've shown there. And let me take the full quantum state of the theory. This represents the spin, the experimentalist, the laser, and everything else in the universe, right? That's what you do. You're going to solve I d chi dt equal to h chi is the full quantum state of the theory. What we're going to do is create a macroscopic superposition. This, of course, is very easy, right? It's very hard to create macroscopic superpositions that are quantum coherent. I don't care about quantum coherence. I'm going to just create a macroscopic superposition. What I'm going to do is I'm going to measure the spin along the y direction. And depending upon the outcome of the measurement, I'm going to send the laser along different directions. Okay. So what I mean is that I have my initial state that's spin along the x direction. And now let me measure the spin. Okay, I do a measurement. The experimentalist does a measurement. If the experimentalist's head says, spin was up along the y direction, I'm going to send a laser to the top. Now, if I make this measurement and then this quantum evolution gives me spin down. My head says spin down. My thing turned. I'm going to send the laser to the right. That's it. Nothing complicated going on. Now comes the important point, right? In linear quantum mechanics, if I simply obey usual unitary quantum evolution, the full quantum state of the theory is chi equal to spin was up, that is the state u, the laser went to the top, and the rest of the environment of the world got entangled with the laser going to the top, that is E sub t, plus spin going down, the laser went to the right, and the rest of the environment got entangled with the laser going to the right. Now, in linear quantum mechanics, we usually do this thing called projective measurement or wave function collapse, crap like that, which basically means we take the attitude, look, because these two states can't talk to each other anymore because of this macroscopic entanglement that we have created, I can simply ignore the evolution of the rest of the state, right? So if you saw spin go up, the laser went to the top, you don't care that there's a part of the wave function where spin went down and the laser went to the right. You can just ignore it because anytime you're computing anything in your world, the inner product between the environment to the right and environment to the top is 0. So all of those terms never matter. So you can completely ignore the rest of the state. So you can effectively say, oh, look, the wave function collapsed. That's where the wave function collapse comes in. That's a prediction of quantum mechanics, though. Okay. Unitary quantum mechanics predicts that this is what the state becomes. All right, so let's now do the simple example and see what happens in this world. So in this world where spin went up, laser went to the top, and spin went down, laser went to the right, what you will see is that in the case where the spin went up, right, if I have a photodetector in there, the photodetector at the top will be hot. That's where the photons are seen. The photodetector to the right will be cold because no photons are seen there. And the spin goes down, the photodetector to the right will light up, the one to the top will not light up. More formally, this is because of the fact that if I want to understand which photodetector lights up, I will be computing the time evolution of the system with the interaction term A mu psi bar gamma mu psi. Everything there is an operator. And if I want to understand why it is that in the world where the photon went to the top, the photodetector to the right does not light up, it is simply because if I compute the transition matrix element T A mu x sub RT, where a mu x sub R is basically the electromagnetic field to the right, that transition matrix element is 0. That is why when the photon goes to the top, the electrons that are in the right, the photodetector don't light up. Very simple. But notice, if I compute the expectation value of the electromagnetic field of a mu x sub R, no matter what the environment is, okay, the expectation value a mu xt and the expectation value a mu xr are non-zero, irrespective of the environment. Right? The environment gets traced over when I compute this expectation value. So there'll always be one term that is non-zero in both cases. So what happens in nonlinear quantum mechanics? In nonlinear quantum mechanics, I've added this expectation value in there, right? It's not the operator anymore, it's the expectation value. And so that is now giving me a state-dependent nonlinear term at order epsilon. So again, as we said, no matter where the laser goes, the top or the right, this expectation value at xr and xt is always non-zero. Which means what you're going to find now is that when I am in the world where the spin went up, the laser went to the top, the photodetector on the right will get hot at order epsilon, because at order epsilon, it is now sensitive to this expectation value. This expectation value now is non-zero. Similarly, in the world where spin went down and the laser went to the right, the expectation value of the electromagnetic field at the top is non-zero. So at order epsilon, I will now be sensitive to something going on, right? So this is kind of what Polchinski also realized in this particular framework, where basically this is communication between the worlds, right? So in linear quantum mechanics, you create entanglement. These two worlds don't talk to each other anymore because all the cross terms kill each other. While now, when I put in the nonlinearity, it now allows different worlds to communicate with each other. This is a consequence. And in fact, you can show that this is a consequence of causality, because essentially you are tracing over the environmental degrees of freedom because of this particular summation form in which I actually had it. And so this is a very important fact, because now you are learning that the nonlinear quantum mechanical effects are visible despite environmental decoherence, right? Normally, to see linear quantum mechanical effects, you need to maintain quantum coherence. But here, even though there is macroscopic decoherence, you can still see the effects of quantum evolution. So Polchinski called this the Everett phone, and this is a very natural way of getting that in this sort of field theory framework. So let's now talk about constraints and tests of this framework, right? So let's go back to the Lamb shift, right? You're of course thinking, my God, what is this guy talking about? The Lamb shift has been tested to 13 digits. So how well tested is this particular framework by all these tests of the Lamb shift? So it is indeed true that if you take a proton and you put it at a point and you compute the nonlinear evolution, due to the shape, the 2s and the 2p levels, the 2s and 2p levels have different charge distributions, and they'll have different expectation value of the electromagnetic field. So if you go and compute the Lamb shift, there will be a level shift, there will be a level splitting. And you might think this parameter epsilon should be extremely constrained by the fact that the Lamb shift has been known to like 13 to 14 digits. Except there's an extremely important fact about nonlinear quantum mechanics, which Weinberg totally messed up. In linear quantum mechanics, we are able to decouple the center of mass motion from relative motion. We do it all the time, right? So what this practically means is that I could take a hydrogen wave function and I could spread that over 1 meter cube, or I could localize that to, I don't know, like a micron cube in some atomic trap. What you do is you go to center of mass coordinates where you decouple the center of mass degree of freedom from the relative coordinate. And then the energy of the atom only depends upon the relative coordinate. The center of mass energy does not matter at all. That's why you don't really care how spread out the center of mass wave function actually is.
Yeah.
But that is it. What?
Go on. I'm trying to ask, you are saying the proton wave function is spread over some region. In this case, this proton is not at focus location, right? In some region, what's when you calculate the observable, what's the wave function you're assuming for the proton? Wait. So what I'm going to tell you now is that in linear quantum mechanics, it does not matter what the wave function of the proton is.
right?
Okay.
That's a true statement. In nonlinear quantum mechanics, it's going to matter a lot.
Okay.
Because in nonlinear quantum mechanics, notice what I wrote. I wrote an expectation value of some operator in the state. That, of course, cares about how that state is distributed. So if I take an electron and I spread it around by 1 meter cube in an atom versus an electron that is localized to a micron cube, the expectation value of the electromagnetic field is dramatically different. In the case where the electron is in the atom and the atom is spread over a meter cube, that expectation value is extremely suppressed compared to what it is in the case of a localized atom.
Okay.
So you cannot decouple the center of mass motion from the relative motion in nonlinear quantum mechanics like you are used to in linear quantum mechanics. So if you ask, how do we actually measure the Lamb shift? We're not measuring the Lamb shift by taking a proton and hammering it to a point. What we do is put it in some trap. The trap has some 100 nanometer size. And it turns out that actually in a neutral atom, literally what's happening is that the atom is going everywhere within this 100 nanometer region. And the electromagnetic field is getting canceled, right? Because it's a neutral atom. So the proton's charge will also be equally spread out. So the electromagnetic field completely gets screened. So even though you have tested the Lamb shift to 13 digits, in this particular theory, it turns out that there is no bound from the Lamb shift on this because of this spreading, okay? So epsilon is less, I mean, like very, very aggressively, if you decide to do a very, very aggressive sort of limit, epsilon is maybe 10 to the minus 2, okay? It probably is more like 0.1.
Okay.
So even though the Lamb shift has been tested so much, there is no bound on it on nonlinear quantum mechanics.
Okay, got it. Thank you.
Great. Similarly, you might have thought that there should be extreme tests of this kind of nonlinearity from nuclear physics, right? We have tested all kinds of nuclear properties. But again, the key point is that if you take a nucleus and hammer it to a point, if these effects exist in QCD, which again, we can add, there will be all sorts of effects. But in reality, the nuclear wave function is spread in like in any system to at least an angstrom. And all of the QCD effects are automatically damped by that spreading. So there isn't a bound at all on this stuff. So it's crazy, right? That we have tested quantum mechanics, we think so much, yet there is no actual bound on this theory. The leading constraint we could think of is basically that if people have trapped ions in like various traps. So if you thought there was a repulsive interaction, this epsilon was positive or something like that, then if you take an ion and you put it in a trap, this Coulomb self-repulsion will try to push that ion away from that trap. So then epsilon is constrained to be less than 10 to the minus 5. But for an attractive interaction, that doesn't even exist, right? So there is no direct limit on epsilon less than 0 for an attractive interaction. So how can we test this, right? So let me quickly tell you some of the experiments that are going on. So here's the thing, right? Naively, when you think about testing quantum mechanics, you are thinking, I'm going to go to an atomic system and make very, very precise spectroscopic measurements. Wrong answer. A precise spectroscopic measurement always involves atoms and nuclei that are spread over some distance, and that spreading naturally just damps out quantum effects, this nonlinear quantum effects. But it's not that this stuff is difficult to test. We're talking about how I can create a macroscopic superposition and still see the effects of nonlinear quantum mechanics. So here is what we're going to do, right? So this is an experiment that's kind of happening right now. So I'm going to take a spin and make this measurement, okay? Spin up or spin down. If I get spin up, I'm going to, I'll basically have a magnet and a squid, okay, a magnetometer. So what we're going to do is the following. Say I have spin up. If I get spin up, I'm going to turn on a magnetic field between time t and t plus dt, and turn it off between time t plus dt and time t plus 2 dt. So let's say if I get spin up, I turn on a magnetic field from 10 a.m. to 10:10 and turn it off from 10:10 to 10:20. If I get spin down, I'm going to turn off the magnetic field between 10 a.m. and 10:10 and turn it off and turn it on between 10:10 and 10:20. In linear quantum mechanics, if my nonlinearity was not there, in the world where spin was up, the squid will basically say there's a magnetic field from 10 a.m. to 10:10, and from 10:10 to 10:20, no magnetic field. Spin down, 10:10, from 10 to 10:10, there's no magnetic field. Between 10:10 to 10:20, there's a magnetic field. But if the nonlinearity existed, in the world where spin was up, I will now find there's a magnetic field, a small magnetic field between 10:10 and 10:20, which is a statement that the other world where the spin was down is now communicating with me. Okay, so that is something that my colleague Alex Sushkov at Boston University is doing right now. You can also do similar tests for gravity and QCD. So for gravity, what will actually is going to happen is that Jason Hogan at Stanford is going to do something very similar. Depending upon the outcome of a spin, he's going to take an accelerometer, okay, and move a piece of mass. So basically, if spin was up, he will move, let's say, a truck next to his accelerometer. If spin was down, he's going to move the spin far. He's going to move the truck far away. And then the idea is that you're going to try to see the truck in the other world at order epsilon with your accelerometer. It's a very similar sort of setup.
That's Page and Gallagher's experiment, right?
I couldn't understand what you said.
I'm sorry. Page and Gallagher did that experiment.
Yes. So there's a key point there, which is that first of all, their experiment was only at order. They didn't really do a great job, so they would only test the parameter epsilon to order 1. But it appears that in fact they made a mistake in how they set up their quantum split. It's extremely important that the splitting is dominated by quantum statistics and not classical statistics. So I have not personally verified this claim, but I've heard from other people who say that when they created the spin splitting, right? The question is, when they created that splitting, were they dominated by quantum noise, short noise, or were they dominated by classical noise? And what I've heard, okay, secondhand, is that in their particular setup, apparently they were dominated by classical noise. But I agree that this is the sort of setup that they tried. It's more like we can now get many more orders of epsilon than what they tried to do. Their constraint on epsilon, even if they had been dominated by quantum noise, would have only been something at the order 1 level. They didn't do a particularly deep job of it. Right. So the other thing is there's one more test you could do, which basically is that you can actually do interferometry. And see it in that. So let's say you take an ion and you split its wave function. And in linear quantum mechanics, the different arms of the interferometer don't talk to each other, right? That's just the Coulomb, the ion doesn't talk to itself. But in nonlinear quantum mechanics, when I take this wave function and split it, the different arms of the interferometer will put out Coulomb fields, and the Coulomb field will interact with the ion itself, right? So the Coulomb field of one path will interact with the charged particle on the other path. And so what this gives rise to is an intensity-dependent phase shift. So depending upon how much of the ion, how much the wave function was split, right? I put it as p n squared root of 1 minus p squared. Depending upon the value of p, I will now get a phase shift that depends upon it. This does not exist in linear quantum mechanics. In linear quantum mechanics, no matter what you do, right? Because the particle doesn't talk to itself, the whatever phase shift I measure in that experiment is independent of how much of the wave function I put in which part. So this is a great way to eliminate all kinds of noise because all fundamental standard model sources of noise will contribute will have a intensity independent contribution to phase shift. Here it will clearly depend upon the intensity. So you can use that to combat systematics. And that's an experiment going on at Berkeley right now by Hartmut Hafner. So this is the final part of my talk, and I'm sorry for going somewhat over. But there's one thing that I haven't mentioned yet, which is that these nonlinear quantum mechanical effects are extraordinarily sensitive to cosmology in a way that even really surprised us. Here's what I mean, right? So you take your Lagrangian, and what we said is I'm going to add this expectation value of the field operator in there, psi bar gamma mu psi. And here is the state. Here's just what it is. Remember, we have to allow for all kinds of superpositions in quantum mechanics. So suppose the state of the world, of the universe, was alpha times our universe. Our universe meaning where I'm sitting here and talking to you, okay, and all this kind of stuff, plus beta times some other world, right? In quantum mechanics, I can create that superposition. M could be some crazy multi-word state or whatever. I mean, I just mean some totally different quantum state. So what that physically means is that at this point X in space-time, right, there is one quantum state U where I'm sitting and talking to you that has coefficient alpha. And then there's another state M, which is some other state where I'm not here, we're not here, nothing else is going on. Maybe it's just a vacuum. In linear quantum mechanics, you never care about the value of alpha and beta, right? But in nonlinear quantum mechanics, you're going to. Because if I now compute the expectation value of chi a mu chi, that's now going to be alpha squared u a mu u plus beta squared m a mu m. And let's say I'm doing one of these experiments that Surjeet is doing, whatever it is. Only in our world is there a laser field being turned on. In the world M, this is empty space. There's no one out there. Nothing is happening, which means that this expectation value, right? So when I do all of my experiments, spin up, spin down, all these things, whatever expectation value I'm creating will be proportional to alpha squared. Now, if alpha is small, just because the Almighty was unkind, he decided that I am so irrelevant that I'm going to make alpha small, just for the heck of it, right? And that the majority of the wave function is where beta is large. Then all of these nonlinear effects will be suppressed by alpha squared, right? This is completely different from linear quantum mechanics, because in linear quantum mechanics, you never have to worry about the value of alpha, precisely because of the following fact. If you want to time evolve the quantum state, right? Alpha u and the state u, they evolve exactly the same way. Alpha is just an overall multiplier. So in linear quantum mechanics, it doesn't matter if our world alpha has epsilon of 10 to the minus 25, 10 to the minus 10,000 or whatever. Linear quantum mechanical evolution doesn't give a damn. But in nonlinear quantum mechanics, if the Almighty put you in a small value of alpha, that's it. You can't do anything about it. All of these experiments that I talked about will give you zero results. So to some extent, we may say that it could be that quantum mechanics is fundamentally nonlinear in many ways, but all of these local experiments so far have only revealed linearity because alpha is extremely small for some reason. We can ask the question, is it possible to somehow boost these results? Can I come up with ways in which no matter what the value of alpha, can I enhance my result? What you might be tempted to do is you might say, let me take my projection operator and divide it. Sorry, let me take my expectation value and divide it by some projection operator, right? But I create some operator that conditions myself on being in the environment U. Can I do something like that? But notice I cannot do that in a local theory. In a local theory, the environment is not a local degree of freedom. So I cannot do this division, right? There is no operator that will solely condition myself on my environment, precisely because the environment is not a local object. So in a local theory, I cannot boost the effects of nonlinear quantum mechanics. So if the Almighty gave you a small value of alpha, too bad. Okay. So I think this is actually a generic feature of local nonlinear quantum mechanics. So with that, let me conclude, right? So I didn't mention one fact because I knew I'd be going over time, which is that even in the case where all of these local experiments give null results, it turns out that there are gravitational effects that are there because the metric field is non-zero in all these universes. So no matter what's happening, even in this multiverse scenario, if these nonlinearities exist in gravitation, there are a number of cosmological measurements one could actually make. I don't have time to discuss it, but I'm happy to chat about it if you guys are interested. But that's a separate and very interesting topic by itself. So this is kind of where we are in our story, right? I think it is very reasonable that quantum field theory can be generalized to include nonlinear state-dependent evolution. I don't see any obvious reason why this is stupid. Conventional tests of quantum mechanics in atomic and nuclear systems are very poor probes of causal nonlinear quantum mechanics. That's one of the biggest things that I learned. But this is not that it's untestable. It's in fact testable in very reasonable ways by the experiments that we have proposed and are actually happening. And the extraordinary cosmological sensitivity of this means we need more experimental ideas on how to test those cases as well. And as I was saying, it does in fact appear to be possible to do this because the metric state, because the metric in general has a non-zero expectation value no matter what you do. So you actually end up creating very funny, nonlinear sort of effects in gravitation. So that's something that David Kaplan and I are working hard on and trying to understand. So that's kind of where we are in our story. So with that, let me stop and I will take questions, more questions.
All right, let's first thank Surjeet for a nice review and entertaining talk and taking lots of questions. We certainly were on board. Marcus wants to say something.
Yes.
Question. So in the cosmological scenario, let's suppose we are in a very, very unlikely universe, but there are some other very, very likely universes, overwhelmingly likely, right? And so
yes.
Those would be, I don't know what they are, but there would be some effects order multiplied that would be proportional to epsilon.
Absolutely.
Perhaps just one, because maybe, you know, the other universes are, you know, almost certainly the most probable ones, for example, right? So in some way, you could say, well, it washes out the effects that you're trying to measure, but you may also expect that it gives you a lot of effects.
Absolutely.
That you can't predict. But,
yes.
You know, they might have hit you in the face. I don't know, a satellite traveling in inner space, you know, it goes by something that's there in a lot of other universes and suddenly just takes a right turn or something, right?
Yeah, indeed. So these are the kinds of tests that we have in mind. So we have, like, I would say 2 kinds of tests depending upon how many of those universes exist. So if there's, like, you know, some power law number, one of the things you could look for is basically cosmic rays, right? So let's say these other universes have cosmic rays in them. So you could go deep inside the Earth and see if there is a high energy cosmic ray that shows up, let's say, an ice cube. Okay, like a high energy proton in ice cube that could not have possibly come from our world at all. But it's exactly as what Marcus is saying, that maybe there is some expectation value of the proton field, right? From the other, this other multiverse or whatever it is, and that could pop up in the middle of nowhere. So those are one kind of thing you could test. The other thing that is extremely resilient to sort of quantum dilution is expectation values of scalar fields like the Higgs. So if there are all these other universes with all these Higgs fields, the expectation value of the Higgs need not be 0 in general, and there could be pollution of the Higgs coming in this way. So maybe it allows us to solve the hierarchy problem in different ways. So this is something that David and I have been talking about, and, you know, we haven't done anything serious. It could open up, you know, so here's what the thing is, right? This is what our excitement is really in some sense. It's the fact that this thing is allowing us to put the expectation value of the quantum field in the state itself. So maybe it opens new directions to solve the hierarchy problem, new directions to solve the cosmological constant problem, because one of the major problems in trying to solve the CC is that I can't measure this vacuum energy in any way other than just gravity. But now I can put an expectation value maybe on the T mu nu in some way, right? So, so we've kind of begun playing with these things. What we are most excited about is that there's a very natural way, it turns out, to solve the black hole information problem. Because no matter what you do, you get this extremely interesting feature, right? So if you take the standard Schwarzschild geometry, why is the horizon not a special point? The reason why the horizon is not a special point, of course, is because it's a, you know, it's a coordinate singularity. Why is it a coordinate singularity? It's because the place where G00 vanishes is the same place where GRR goes to infinity. So the determinant is going to be non-zero, which is why everything works. But now let's say your space-time is a linear combination of the standard, our world, plus some other space-time. Now notice that if I put this expectation value, the place where G00 actually vanishes is not the same place where GRR diverges, right? Because this epsilon has changed those things a little bit, which means you actually end up getting a physical singularity at the scale of the horizon. So it trivially would create a firewall in a very simple way. And it would actually show up as some sort of a hair to black holes. So we are actually extremely interested in testing these things with Event Horizon Telescope, with LIGO, things of this kind. You know, so it's a very testable scenario. It does not show up in Alex Surshkov and Hafner or Jason Hogan's experiment, but it will show up in other experiments. And perhaps, indeed, it will show up in cosmic ray detectors as well. So this is, I think, a pretty rich area in terms of thinking about it, both experimentally and theoretically. It's just a new tool to play with.
I have that's probably not visible here. Yeah. I have a question that's related to that. If you think about your your cosmological slide where you have a superposition of two different universes, you're calculating the expectations value, say, of AU. What you want is AU of X, function of position.
Yes.
In order for that to make sense, you have to know what X here is compared to X in some other universe.
Yes.
That's one of the basic problems in quantum gravity. We have no idea how to do that.
No.
How do you say this point here is the same as
very good
some point in another universe?
Very good. So we would take this point of view that the space-time manifold is a real thing, right? There is an X that's defined on it, and the quantum states just live on top of it. Okay, so X is fundamentally just a label, right? So you take your initial state of the universe, whatever it is, and there is an X in it. And now there's an important point. Normally, when you create these different superpositions, as you're saying, I can do a coordinate change in one universe that doesn't care about the coordinate change in some other universe.
Yeah.
But you can't do that anymore. When you have the nonlinearity, you have your initial manifold, 3 plus 1, you do the 3 plus 1 thing of general relativity or whatever. You define your initial time slice. There's an X in there. And these are just quantum states that live on it. So when you do a coordinate change in one universe, because the manifold itself is fixed, it actually changes coordinates everywhere. So there isn't really, it's only, I'm not taking your extreme geometric viewpoint. I've never liked that viewpoint. And I would say that the correct way of doing it is precisely by actually saying that there is an underlying space-time manifold. X is very meaningful. It has to be meaningful. It's a local theory. The quantum state just lives on it. If you think about it in that language, there is really no problem.
But then you get back to an infinite degeneracy, right?
What infinite degeneracy?
Take the same manifold. You choose two different sets of coordinates. That gives you two different states.
No. So the
first argument was that
you have one. You can choose whatever metric state you want on the thing, right? But on the manifold, X is not a state, right? X is not a state in quantum field theory. X is just a label.
Right.
Right. So you're free to pick whatever coordinate system you want on the manifold. Totally, completely agree with you. But once you've picked a particular coordinate system, you now build your quantum states on top of it. Now, you are correct that normally what you do is that I have universe A and universe B. I can choose whatever coordinates are convenient for me in universe A and whatever coordinates are convenient for me in universe B. That's all true. I'm not denying that. But in this case, anytime you do a coordinate change, of course, you have to do the coordinate change of the full manifold, which means you change the other quantum states too. It's a more clunky description, perhaps, in some sense, but there's no fundamental problem.
Okay, so your picture then is that even when you have a superposition of different states, they are living on the same manifold.
Yes. And the metric is just simply a quantum state on the manifold.
Are you sure that you can get one-to-one correspondence, even if the two will have different energy momentum distributions?
What do you mean by one-to-one correspondence?
I mean, the universe, you want to say this manifold is real, right? It's not just coordinate. So that means one point in this universe is exactly mapped to the other point in the other universe. Yeah,
because the underlying geometry is the same, right? So I would say, I should say the word geometry. That's a wrong word, right? So the main point to understand is that all of the things that we are talking about, right? Expectation values of A, mu, things of that sort. Remember, they're tensors. A tensor is something, or a vector. These things have meaning independent of the metric I put on the state. These are things that you can define on the manifold. They have a meaning independent of any kind of geometry that I choose, right? And so because I'm using fundamentally geometric quantities, I don't care what metric you put on it. The transformations will work properly.
You still need the same asymptotics.
Pardon?
You still need the same asymptotics.
Yeah, I mean, if you take an asymptotically flat space, that would be okay. But I think you can even do this in cosmology. I don't see a problem with it.
Yeah.
I have another question. In quantum mechanics, the wave function normalization doesn't matter, right? You can multiply by any number, but here you do care, right? So do you always normalize the wave function to some particular values to one?
So right. So so the thing is that the norm of our state is conserved. You can prove that because the evolution is still Hamiltonian. It's a Hermitian evolution. So no matter whatever the initial norm of the state is, the norm is conserved by time evolution, right? So this normalization you're talking about is only important at the end of the day to define probabilities. That's an interpretation that we're trying to do. So effectively, the way would be the fact that when I'm trying to define a probability, I'll just divide my result by the norm. So because it's a conserved norm, it never really matters per se. It's because my time evolution preserves the norm. That you can explicitly prove. So you are right. Like I cannot necessarily say that the norm is 1, right? That I cannot do because I don't have that rescaling freedom that you're correctly pointing out. But why do I need it? I only need to define a probability.
All right. So is there any more questions, guys? So maybe in the light of time, we can thank Surjeet again.
Thank you very much.
And hopefully we see you soon in person.
In this universe. Let's not go to a different universe.
In this universe.
In this universe, yeah.
Well, the other universe is fine as well. You know, if we can move in there with you too. So
that's true. That's true.
You know, maybe in the